Everyone wants the one control that stops every attack. Does it exist?
It doesn't. Lean on a single defense, and the day it fails, everything fails with it. So this series assumes the opposite, that any one layer can and will miss. The answer is depth. Several independent layers, so one miss never becomes a breach.
Resilience instead of a perfect wall.
Exactly. That's what layered resilience means, and it's what this series is about.
So what are the layers?
First, runtime containment, bounding the damage when prevention leaks. Then isolation, walling off data, memory, and execution so a breach can't spread. Then safe deception, decoys that turn an intruder's own moves into a signal. Then drift detection, spotting when the agent's behavior quietly changes. And lifecycle gates, enforcing policy at every step, from input to output.
5 layers, each covering the other's gaps.
Right. No single one is trusted to be perfect. Together, they hold.
And when something does slip through,
One mistake happens. A classifier misses. A tool gets tricked. But the layers absorb it. What one misses, the next catches. So the mistake ends up a near miss, contained, spotted, and survivable.
the cost of a miss stays bounded.
That's the whole idea. By the end of this series, you'll know how to build agents where one miss never becomes a breach.
So we put a classifier up front to catch the bad requests. Doesn't that just solve it?
It starts with the stream of requests coming into the agent, the part of the system that actually takes action on our behalf. Up front, we place prevention, a filter that tries to catch the harmful requests before they ever run.
And most of the time that works.
Most of the time, yes, the obvious bad ones get blocked cleanly. But no classifier is perfect. Some harmful requests look completely benign, and they slip straight through.
So prevention on its own isn't enough.
Right. If that filter is your only line of defense, whatever it misses runs with nothing left to stop it.
If prevention leaks, what catches the leak?
Keep prevention. It still does the heavy lifting, catching most of the harm. But put a second layer beneath it. Whatever prevention misses falls down to here. That layer is containment. It doesn't try to judge intent. It simply limits what any action is allowed to do.
So even a bad request that got through can't do much damage.
Exactly. Two independent layers. If the first fails, the second still holds. That's defense in depth. Never trusting one control to be perfect.
What does containment actually do to an action?
Picture a boundary drawn around anything the agent tries to do at runtime. Inside sits the action itself. Say, a tool call that reaches out to do real work in the world. The boundary caps what it can touch. It gets a scoped token, permission for exactly this task, and nothing more. It gets a time limit, so a single action can't run away or hang forever. And it's held to a fixed set of allowed targets. It can only reach what it's explicitly permitted to reach.
So even a hijacked action is boxed in.
That's the idea. The action still runs, but only ever inside walls it cannot push past.
Put a shape to it. What's the payoff?
Without containment, one action that goes wrong can reach everything the agent could ever touch. The blast radius, the damage a single failure can cause, is the whole system. Add containment, and that same failure is boxed into one tiny slice.
The mistake still happens, though.
It still happens, but now it's a contained incident instead of a full breach. You shrink the blast radius from everything to almost nothing.
When containment catches something, what can it actually do about it?
At the center is the runtime control, the thing watching each action as it runs. If an action crosses a line, it can hit a kill switch. Stop that action instantly, mid-flight. It can roll back, undo the partial work, so the system returns to a known good state. Or it can quarantine, freeze the agent and hand off to a person before anything else happens.
So it's not just blocking, it can respond.
Right? Containment isn't a wall you simply hit and stop at. It's an active response that limits the damage and recovers from it.
So what's the mindset shift here?
The tempting design is to trust prevention, assume the filter caught it, and let the action run free. The resilient design assumes the opposite, that something did get through, and contains every action just in case.
Plan for the miss, not the catch.
Exactly. You stop asking whether you caught it and start asking, if you didn't, what's the worst that can happen? And you make that worst case small. Prevention lowers how often things go wrong. Containment decides how bad it gets when they do.
When an agent gets compromised, why does it so often become a total loss?
Because so often everything lives in one shared space, a single place where all the agent's parts sit together. There's the data it reads and writes. There's its memory, what it remembers across steps and across sessions. And there's execution, the code and tools that actually do things in the world.
And they're all in the same room.
So the moment one part is breached, the intruder can reach all of them. One foothold becomes total control.
So, what's the fix? How do you break up that shared room?
Give the data its own home, a store the rest of the system can't just wander into. Give memory its own home too, walled off from the data and from the tools. And give execution its own sandbox, an enclosed space where code runs without touching the others directly.
3 separate places instead of 1.
With real walls between them. Now a break-in on one side doesn't quietly open the others.
But the planes still need to talk to each other, don't they?
They do. Start with the data the agent needs. Between it and everything else sits a gate, a checkpoint that decides exactly what's allowed to cross. Only what passes reaches execution, where the actual work happens. And another gate stands between execution and memory. So what gets written into memory is checked too, not just anything the tools happen to produce.
Every border has a guard.
Right. The planes cooperate, but only through controlled crossings, never a free-for-all.
Show me the difference when something does get in.
In one shared space, a single breach compromises everything at once. There's nothing to stop it spreading. With isolated planes, that same breach is stuck where it landed. One plane falls, the others stay clean.
So the damage stops at the wall.
Exactly. Isolation doesn't stop the break-in. It decides how far the break-in can go.
Inside a plane, how tight should the permissions be?
Take one execution path, a single task the agent runs. The lazy option is to hand it a master key, access to everything, just in case. The disciplined option is a scoped key, permission for exactly this one task. That key opens only the data this task genuinely needs, and nothing beyond it.
Least privilege, per path.
Right, so even if that one path is hijacked, the key in its hand barely opens anything.
Bottom line, what does isolation buy you?
Without it, the reach of one breach is the whole system, everything the agent could ever touch. With it, that reach collapses to a single plane, a small fraction of the whole.
The breach still happens, though.
It does, but isolation decides how far it travels. And that's the difference between an incident and a catastrophe. You can't prevent every compromise. You can make sure no single one owns everything.
Deception sounds sneaky. What's the honest version of it?
Start with a real resource, something the agent legitimately uses to get its job done. In normal operation, a genuine user reaches straight for it. That's the only path real work ever takes. Now set a decoy beside it, something that looks just as real, but that no legitimate task ever needs.
And no honest path ever goes there.
So if anyone reaches for the decoy, it's almost certainly an intruder poking where they shouldn't. That single touch trips an alarm. A tripwire only a bad actor would ever hit.
Where do you actually put these decoys?
Scatter them through the real estate. Here are the genuine assets, the data, files, and services the agent truly uses. Now mix in decoys that look identical, a fake database, a fake file, a tempting fake key.
And an attacker can't tell which is which.
That's the point. From the outside, they're indistinguishable, so an intruder has to gamble. And every fake they touch gives them away. The real work, meanwhile, only ever knows the genuine ones, so it never trips a wire.
What happens the instant something touches a decoy?
Any access attempt comes in, someone or something reaching for a resource. If it lands on a decoy, that's a path no honest task ever takes. So it fires an alert immediately, a high-confidence signal that something is wrong. And that signal can drive a response, isolate the session, freeze the agent, pull in a human.
So a touch isn't just noticed, it's acted on.
Right? The decoy converts a quiet intrusion into a loud, actionable event.
Decoys catch a touch, but can we make the attacker waste time too?
Picture an intruder who's gotten in and is hunting for something valuable. The environment offers them tempting paths, a promising door, a vault that looks worth cracking. Every one of them leads to a dead end. There's nothing real at the far side to steal. Meanwhile, the clock is running and every move is tracked. They burn effort and expose their methods.
So the maze works against them.
Exactly. Dead-end paths turn an attacker's own persistence into wasted time and a richer trail of evidence.
How trustworthy is a deception alert compared with normal ones?
Regular monitoring throws a lot of false alarms. A false positive is a warning about something that turns out to be nothing. A decoy is different. Because no legitimate task ever touches it, an alert from it is almost never a mistake.
So you can actually trust it.
That's the real gift of deception. A signal clean enough to act on immediately, without second-guessing. High confidence, low noise. That combination is rare and valuable in security.
Sum it up. What does deception really change?
By default, an intrusion is silent. An attacker slips in, and you may never know until the damage is done. A deception layer sits in the middle, decoys that shouldn't be touched, and dead ends that lead nowhere. It turns that silent intrusion into a loud, high-confidence signal, and into intelligence about how the attacker operates.
So probing the system becomes a mistake for the attacker.
Exactly. You make hostility reveal itself. The very act of poking around is what gives the intruder away.
Before you can spot bad behavior, don't you need to know what good looks like?
Exactly. You start by learning the agent's normal range, the band of behavior it shows when everything is healthy. That's the baseline. How many tools it calls, how much data it moves, how long it takes. Day to day, its readings sit comfortably inside that band.
So normal isn't one number, it's a range.
Right. A healthy band with a little natural variation. Everything that follows gets measured against it.
What does trouble actually look like on that chart?
Sometimes it creeps. Early readings still sit inside the normal band. Nothing alarming. But each one drifts a little further from center. This is drift. A slow, steady move away from normal. Left unwatched, it eventually crosses out of the band entirely. And by then, the behavior has quietly changed for good.
So the danger is that it's gradual.
Right, no single step looks wrong, which is exactly why slow drift slips past anyone only watching for big, obvious jumps.
And the opposite of slow drift?
A sudden anomaly. For a while, the readings are steady, sitting right where they should. Then, out of nowhere, one spikes, a single moment wildly outside the normal range. Just as fast, it can settle back to normal, as if nothing happened.
So that one you can't afford to blink on.
Right. A spike is a loud, instant signal, often a sign of a tool being abused or an injected instruction firing.
So what signals actually tell you the agent is drifting?
Put the agent's behavior at the center and watch a handful of dials around it. Tool calls, how many it makes, and which ones. A surge or a strange new tool stands out. Data volume, how much it reads or moves. A sudden flood is a red flag. Target reach, what it's touching. Reaching for resources it never used before is suspicious. And timing, its pace, and the hours it works. Activity at 3 in the morning, when it's normally idle, says something.
A few honest signals, watched together.
Exactly. No single dial is proof, but together they paint a clear picture of normal versus off.
How does this run in practice, day to day?
It's a loop that never really stops. First, Learn the baseline, capture what healthy looks like. Then watch the live behavior as the agent works. Constantly compare the two. Is what's happening now inside the normal band or sliding out of it? When it drifts, act, alert a human, tighten limits, or contain the agent. And that experience refines the baseline for next time.
So it keeps learning what normal is.
Right. Normal isn't frozen. The loop keeps the picture current as the agent and its work evolve.
Why does catching drift early matter so much?
Every problem has a moment when the behavior first starts to drift. Good monitoring catches it right there, early while it's still just a small deviation. Without it, the same drift runs unchecked until it finally becomes a full incident. The gap between those 2 points is the window monitoring buys you back. Time to act before real damage is done.
So you're trading a big incident for a small alert.
Exactly. The whole aim is to see the change before it becomes damage, and drift detection is what makes that possible.
Most teams put one policy check right before a tool runs. What's wrong with that?
Follow a request through, it arrives, and hits a single gate right before the tool fires. That's the one and only checkpoint. Pass it, and the tool acts.
Seems reasonable enough.
But everything before that gate, the untrusted input, the model's reasoning, ran unchecked. And everything after it, like what the tool returns, is unchecked too. So that one gate is a single point of failure. Whatever it can't see, nothing else catches.
So where should the gates actually be?
At every transition, it begins the moment user input arrives, the first place to inspect. Before the model runs, a pre-model gate on the context you're about to feed it. After the model responds, a post-model gate on what it proposed. Before a tool executes, a pre-tool gate on the action itself. After the tool returns, a post-tool gate on the result. And on the final output before anything leaves, a continuous line of enforcement, from the first input to the last byte out.
Aren't some of those gates redundant?
Not at all. Each inspects something the others can't. The input gate labels how trusted the input is and screens for injection, hidden instructions smuggled inside data. The pre-model gate filters the context by permission, stripping out what the model shouldn't even see. The post-model gate checks the model's proposal before it ever becomes a real action. The tool gates validate the arguments going in and verify the result coming back. And the output gate checks egress, whether this data is actually allowed to leave, given its label.
So they're a chain of specialists.
Exactly. Each one simple and focused. And together they cover the whole journey.
Put the two designs side by side.
A single gate is efficient and brittle. Whatever that one check misses, nothing else catches. And it has to understand everything, from input trust to output egress, which no single check does well. Distributed gates let each one stay simple and focused, and let the system catch a problem at whichever stage first reveals it.
You trade a little efficiency.
For a lot of resilience, efficiency drops slightly. The odds of catching a problem climb sharply. That's almost always the right trade for anything that can take real action.
This is the last piece of the whole series. How does it all fit together?
Think of everything we've built as a stack. Runtime containment catches what prevention misses. Isolation bounds how far any single failure can reach. Deception turns hostile probing into a signal you can trust. Monitoring spots drift before it becomes an incident. And lifecycle gates enforce policy continuously across all of it.
No single layer trusted to be perfect.
Right, stacked, one layer's miss meets another's catch, and the cost of any mistake stays bounded.
So what's the payoff of all these layers together?
Picture an attacker who wants to cause real harm. To get there, they don't beat one control. They have to defeat several independent ones, each watching a different thing. And only then would they reach the goal.
Every one of them has to fail at once.
Exactly. That's what makes the cost of a miss bounded rather than infinite. One mistake becomes a near miss. A signal to act on, not a breach to recover from. No layer is perfect. Together, They make sure no single failure is ever catastrophic.